All right, good afternoon, everyone. So hopefully we can finish up this unit today. So let's just review a little bit about what we were talking about last time. So we are doing multiple linear regression now. We have D different features we are using to predict a target. And we have, therefore, D different slope coefficients we need to determine. And we have this intercept we need to determine. And so in this equation, we're using the I subscripts, which means we're showing what happens to the ith training sample. And the hat means this is our prediction. So we can combine all our training predictions into y hat, all our training features, as well as these ones into this A matrix, and all the coefficients in our model into the beta vector. And we first showed how we can write things using this matrix vector equation. Y hat is A times beta. And then in order to determine what beta are, we first said, what is our criteria for designing them? Our criteria is to minimize the RSS, same as we did last unit. And we said that basically now that means that we are orienting a plane, a d-dimensional plane, so that the sum squared difference between the samples in our training data and the plane is minimized. We also wrote RSS in terms of a norm. And we, like last time, said that the way we're going to solve this training problem is to find the beta vector that sets the gradient to 0. And the gradient is the vector of partial derivatives. In this case, it's the partial derivative of RSS with respect to all our d plus 1 coefficients. So if we can derive this gradient and set it to 0 in closed form, then we can essentially get our beta coefficients analytically. So that's what we started to do. So the first thing we did is we derived an equation for this partial derivative with respect to the jth beta. And we saw that this looks like this for any j. So we want that whole vector to go to 0. That means that this whole vector here must go to 0. And that's essentially what we have here. And then we just sort of moved things around a bit, wrote it as this equation. This is a square matrix. So this has a chance of being invertible. And so if we can multiply both sides of this matrix by the inverse of A transpose A, then we can get this least squares solution for beta. So several people asked, why can't we just do the inverse of A transpose? And that's because A transpose is not usually square, it's usually tall, and you cannot invert a non-square matrix. Okay, so this is one way of getting the coefficient vector. We'll describe another way today. And similar to last unit, we talked about quantifying how good of a fit our linear predictor is. And we're going to do things the same as before with R squared. This is basically 1 minus a normalized version of RSS, such that R squared equals 1 means perfect prediction. R squared equals 0 means prediction no better than the trivial case. And R squared less than 0, that's impossible to do with least squares. Least squares will always get you somewhere between 0 and 1, but it is possible if you do something worse than least squares, or if you train on one data set and then you test on another, you could get R squared less than 0. Okay, and so towards the end of last lecture, we were seeing if we could get an expression that was a bit more insightful than this, similar to how we did it in the last unit where we had statistical quantities like variance, covariance, and so on. So that's what we're doing now. So the first step was to write the beta vector in a slightly different way, where we're grouping all the last d coefficients into this new vector called beta 1 through d, and isolating them from that first coefficient. The motivation there is because these last coefficients, they work differently than the first one, in that these ones are slope coefficients. They operate on x, whereas this one does not. So if we do that, then we have our prediction equation looking like this. And the next thing we did was we started to define some sample statistics that are going to be useful for us. And so the first thing we did is we defined the sample mean of our feature vectors. So this is the vector of features for the ith example in our training data. And we averaged those over all our training data to get this vector. And we said that if we look inside this vector, what we'll find are the sample means of the individual features also when we take the mean over the data. So those are the things we saw in the last unit, scalars. Now we have a vector. The next thing we did is we defined the autocovariance matrix. So here we have xi minus its mean. So that's going to be a column vector. And we take the same thing but transpose it. And so now we have a tall vector column vector times a row vector. That is going to give you a full matrix. And we're averaging that quantity again over the data. And this is known as the autocovariance matrix. When you look along the diagonals of this matrix, you find the variances of the individual features over the training data. When you look off the diagonal at the triangles above and below the diagonal, you find the covariances between the features, like between feature x1 and x2. That would give you the element right here and right here. Okay, then to get the relationship between the targets and the features, we have this cross-covariance vector. So here we have a vector xi minus its mean, yi minus its mean. That's just a scalar. So this is going to be a vector quantity, and when you look inside that vector, you find the same covariances that we talked about in the last unit. So these are the quantities from the last unit, scalar. These are now the vector extensions when you have multiple features. Okay, any questions there? Okay, so I'll be working with those more today. I think the last thing we did was we derived some alternative expressions. So we saw that you can write the covariance, the autocovariance, in terms of this average of the outer products xi transpose minus the outer product of those sample mean vectors. And we can do something similarly with this cross-covariance vector. We can write that as this average minus this product of the means. Okay, and these things will be useful for what we do next. All right, any questions on last time? Okay. So now let's repeat the derivation. This is going to feel a lot like what we did in the last unit, so hopefully it will be familiar. I'm going to go a little bit faster. So our objective now is to compute the RSS derivative with respect to beta 0, the first coefficient. So here is the expression for RSS. Here's that partial derivative. And when we do this, we're going to first move this through the sum by linearity. Then we're going to use the chain rule, differentiating this squared quantity so that we can bring the 2 out from the chain rule, the sum, and now, and then we have also the, sorry, let me see how I want to write this. Okay, so we're going to have yi minus beta 0. This is the term inside the parentheses minus xi transpose beta 1 through d. All of that. And then finally, we have to take the gradient of what's inside the parentheses with respect to beta 0. And so let me see, is Thomas Agre here? Okay, what about Dominic Alexander? Yeah, so Dominic, what would that partial derivative of this with respect to beta 0 be? Just minus 1, right. So that just gives us this minus in front of here. Then we do the same thing, but instead of looking at partial derivative of beta 0, let's look at any of the other betas between 1 and d. So we have, similar to above, we have this expression, but now let's write this in terms of the individual betas, because here we want to take the partial derivative with respect to one of them, which is sort of it's inside here, but it's maybe not exactly clear how it's involved. So let's be explicit. Let's write this as a sum. And when we write that sum, let's make sure not to use j, because j has a particular meaning over here. It's some particular one of these, whereas this j is a temporary variable, or this summing variable I call j prime. That's a temporary variable. That's just different than this one. So that's how we're doing this. And so, again, when we compute the partial derivative, we can move it through the sum, pull down the 2. Then by the chain rule, we have the thing inside the parentheses, which is the same as above. And finally, what do we get now for the partial derivative of the thing inside the parentheses? So let's see, is John Cao here? CAO? Yeah. So, yeah, so what do you get when you do partial derivative of this respect to beta j? So x, so this is a vector. That's not what we want. We want to use something related to this. Okay, so you're right to realize that these are not involved. These do not depend on beta j when j is in this range. But basically what we have here is we have a sum of different xij times beta j terms. And one of those terms will match this j. And all the others won't match, and they won't play any role in the derivative. So when we pull out that one element in the sum that matches, it's going to have xij beta j. And now I take the derivative of that with respect to beta j, and I get xij, exactly. So we have xij over here on the right, and so okay, so that's what we have. Sorry, this my apologies. This should be equation 1. So we have the partial derivatives done. Now we just need to do some simplification. So similar to last time, we want to turn this into a 1 over n so that this looks like an average. And because there's a 0 on the left, we can multiply both sides of this equation by minus 1 over 2n. And that will give us this. We basically have this nice 1 over n here. Now we can recognize things start to look kind of familiar. And in fact, we can sort of distribute this average over those 3 terms. We have an average of the yi's. We know that that's y bar. We have the average of this minus beta 0, but since that's constant for all the i's in the average, that just gives us beta 0, minus beta 0. And then we have the average of this. And here, if you want, you can think of putting a parentheses here because this beta term is not dependent on I, so we can think about it as outside the average. And if we do this average, we just get x bar, and then this is going to be a transposed version. Okay, so is everybody with me so far? Yes?
What happened to the negative on the second part where we put xij? So
Oh, let's see.
equation 2.
I think I had a miss the negative there.
Oh, yeah.
Yes, that's right. The partial derivative is negative xij, and I had forgotten that. Thanks. Okay. All right, so everybody okay with this expression? Okay, and so we're almost done with this first part. So now you can see that 0 equals y bar minus x bar transpose beta 1d, 1 through d. And so that means that beta 0 equals y bar minus x bar transpose beta 1 through d. Okay, so this is our first relationship, which actually is very similar to what we found in last unit. So, okay, everybody good at this? All right, so now let's, so this question mark should say 2. And the next question mark should say 3. Okay, so what we're going to do is start with this equation, multiply both sides by minus 1 over 2n to turn this into a 1 over n. And that will give us this down here. And then we can again distribute this sum. So we get the first term where we have both of these i's are getting averaged. Second term, this is a constant with respect to I. So, but we still have this average. And if you notice, we're averaging over I for a fixed j. So this is going to be x bar j, or the average of the jth feature over all our training samples. And finally, we have this times this, which gives us this. And here I'm putting the parentheses here just to emphasize the fact that we don't have to really think about this beta as influencing this average. Just makes it a little bit easier to parse. Is everybody okay with this expression? All right. And then the next thing we can do is we can put this into here, and that will supply some new terms. This one shows up, and this one shows up. And things are starting to maybe seem a little familiar, except they're a little bit messier because we have some terms that have both I and j indices, other terms have only j, other terms have only I. So that's why this is a little bit complicated. So the key here is to remember that this is just a scalar quantity, everything here. And so if we can think about this as the jth term in our xi vector, so over here, notice I'm writing jth term, and I'm replacing this with the xi vector. Over here, I'm saying that this is the jth term in the x bar vector. This is the jth term in the x bar vector, and then this is the jth term in the xi vector. So making those substitutions, all of a sudden things look a lot nicer inside the square brackets. And maybe you can even see what the answer is. So what about these two terms? What happens when we combine these? So let's see, is Ethan Hartman here? Yeah. You recognize that?
Is that the covariance?
Yes. It's the cross, I think we call it the cross covariance. So we have, it's a vector S with subscript xy. So that is what we get out of this. And then there's another term here. Let's see, Aaron Hoskinson. Is Aaron here? No? Okay, what about Heriberto Nurse? Yeah. So do you recognize what that second one is? So maybe one hint is you can bring this XX transpose inside that parentheses if you subtract it.
The autocovariance?
Yes, it's the autocovariance matrix. So I'll write it over here. This should be a big S. This is a matrix with subscript XX. Oh, and sorry, there's a minus sign here. And then also we have our beta. Beta 1 through D. And this is what's inside the square brackets. Okay. So is everybody good with that? So notice we have a column vector here, and we have a matrix times a column vector, which this is also a column vector, so the dimensions are all matching up. It's always good to check whenever you derive something, make sure the dimensions match up, otherwise probably made a mistake somewhere. Okay, everybody good with this last expression here? Okay, so this should hold for all j. The jth element should be 0. So that means if I consider that happening for all j, so this should be equation 4. That means that entire vector should be equal to the 0 vector. And so from there, we can say equivalently SXY. Actually, maybe I'll write it this way. We could say that SXX beta 1 through D should be equal to SXY. And how do I get beta 1 through D then? Exactly. We'll left multiply by the inverse of this matrix. Okay, is the sanity check, is that a square matrix, SXX?
Yes.
It is, right? Yeah, because if you remember, it was made from the average of the outer product of two identical vectors, so it's going to be square. Is it necessarily invertible? Not always. Usually is. At least when you have more samples than you do features, then it tends to be invertible. Okay, so now essentially we have our second design equation. So we have this one for the beta 1 through D coefficients, and then once you know those, you can get your beta 0, your intercept term. Okay, so the hard work is done. Any last questions on this derivation? Yes.
Should that be an
Oh.
SXY?
Yes. Okay. I was kind of asleep at the wheel here. This should be an SXY. Okay. Sorry about that. Okay, so we have our two equations. All right, so let's put them together. Remember that the overall beta vector is this intercept followed by the rest. So we're stacking them vertically and just plugging in the expression for the scalar beta 0. That will be the first element in this vector on the right, and then the rest of the elements below it are that vector. So that's our least squares solution. This should look kind of familiar to you because in the last unit, we had a special case of this where we had a single feature. And in that case, we would have the beta having just two coefficients, beta 0 and beta 1. And we derived an expression where the top one was y bar minus x bar sxy divided by sxx. Those are all scalars. And then beta 1 was sxy divided by sxx. Okay, so you can see that there is a pretty strong correspondence there. Of course, when you work with scalars, you can just, put something in a denominator. You can't do that with vectors. With vectors and matrices, you have to worry about the order of things. So here we have on the left, we have this matrix inverse. On the right, we have this this vector here, covariance. So, but you can see that if this was a 1-by-1 matrix, just a scalar, then you can just move it down like that to the denominator. And then similarly over here, we have sxx in the denominator. We have an x bar, we have an sxy, so that all works. But again, with vectors and matrices, the order matters. So this is really the order we need for this to be a scalar quantity. We have a row vector, followed by a matrix, followed by a column vector, and that is going to be a scalar. Okay, so everything agrees. It's just that previously we saw a special case the scalar case. Now we just expanded it to the vector case. Okay, great. So any questions on any of this? Everybody good with this? Excellent. So let's move on a little bit. So let's talk a little bit about how you compute this in Python. So we're going to talk about 3 different ways. The first way is to do everything explicitly. So we essentially want to do this, actually all of this, in NumPy. NumPy would be the framework to do this in. So the first step would be to create the A matrix, assuming that we already have our X matrix. The way you do this, actually, the first thing is to create this vector of 1s. So that's what you can do, this NumPy.1s. You're creating a column vector, so it's sort of like a matrix with this many rows and that many columns. Once you have that column vector, you can stack it to the left of this matrix using the hstack, horizontal stack command. So you have to give it the 2 things you want to stack, and they have to be in parentheses. So that will give you your A matrix. The next step would be to implement this. So here, first, you do A transpose dot A. The dot is going to be doing this matrix multiply. And then to invert that, you could use the np.linalg.inverse routine, and that would do this matrix inverse. And then as the last step, you need to do the matrix multiply of this and this. And the way that I'm doing that is at first I'm doing this. This would be A transpose dot Y. And once that's computed, we can do this matrix dot that vector. There's another way to do it with an ampersand command that was added a bit more recently in NumPy. The ampersand gives you matrix multiply directly, so that would be an alternative to dot. Both work fine. But I don't recommend any of this because, for a couple of reasons. The first reason is that this is actually somewhat slow, especially once you get to large matrices. Computing an inverse like this, generally the complexity is cubic in the dimension. You can reduce it to quadratic in the dimension if you do it in a more clever way. And to do it in that more clever way, you essentially kind of do all this together. And that is handled by some efficient numerical linear algebra algorithms that have been developed a few decades ago that are in this LePac library. And in fact, there's a command called least squares here in NumPy that you just give it the A and the Y and then essentially computes this. So that is going to run a lot faster. It's a lot more direct. It's actually more numerically accurate than this manual approach. This actually returns, I think, a pair of quantities. And so what I'm doing here is I'm just pulling out the first thing in the pair, which is actually the beta vector that we want. Okay, so this is a better approach than this first one. However, it's still what I would consider a manual approach and not really leveraging all the tools we have at our disposal for machine learning, which is the scikit-learn library. So I'm going to show you now the recommended way. Part of the reason this is recommended is that once we learn to do this, we will be able to use the same thing when we move on to many other techniques that we're going to learn about. They all have the same style interface. So once you learn it once, you know how to do it in all these other cases. So in this case, we go to the linear model library within sklearn, and that has various tools for linear models, one of which is linear regression, which is what we've been working on. So the first step here is you instantiate this object, which means you run this line of code, and under the hood, it sets up a bunch of stuff in this. So this is an object that has functions, data, many things inside of it, and so this sets everything up. Now that that's set up, you can use the fit command, and you can apply that to your data, your feature matrix and training label vector. And when you run this, essentially what it does under the hood is it does this, and it stores that beta internally. It doesn't report anything. It just quietly computes it and stores it inside so that it's there when you want to use it. You could extract it if you want. And once it's extracted, you could, do like x dot beta. You could do that, but a slightly more streamlined way of doing that is to call its predict function, which takes the internal beta weights as well as the x that you're providing here, and it essentially is doing this x beta. I'll just write it how we typically do, x times beta. It does that, and it gives you here the predicted y vector. Okay. So we're never explicitly accessing the beta. It's all hidden inside. It's there if we want it, but otherwise it's just quietly stored inside. Once we have that vector of predicted labels, we can subtract it from the true labels. We can square all the elements in that vector, sum them to compute RSS. Now we have RSS, and to make that more interpretable, we can convert it to an R squared by normalizing it and subtracting it from 1. We print out the results, and we find, in this case, for this diabetes data set, it's 0.514. So now that we know a little bit more about how to interpret R squared, let's see, is Ashton Keller here? Yeah, so is that, how well did our linear model work?
I mean, it's like slightly closer to 1, but it's a fairly weak linear
Yeah,
relationship.
so basically it's kind of in the middle. It's not far from perfect, far from terrible. So it's somewhere in the middle. So that's what it is. But at least we have now a way of understanding how well it worked, how well our linear model fit this data set. All right, any questions on anything we're doing here? Okay, yes.
Just for clarification, the feature matrix, the I data is your columns, correct? So like the features run.
No, so the rows are always, the I is always coming down the rows, so each row is a new sample in our data set. So the X matrix, every row is a sample from our data set. Every column is a different feature. So like the first column might be blood pressure, the second column might be age, like that. The first row is the first patient, second row is the second patient, third row is the third patient. So
Like if your X vector is your I data, it could be the vector transpose.
So I don't know. So it's kind of like X1 would be transposed, or maybe you could, Python always starts counting at 0.
That's what I meant.
Yeah, so that would be the first one, that would be the second one, and so on. So they're the rows of the X matrix.
Thank you.
Sure. Okay, everybody good with this? All right, so now we know how to do things. Now let's step back and compare the thing we did in Unit 1 and the thing we did here in Unit 2. So in Unit 1, the situation we had a single feature, single scalar feature x. We came up with this linear model that involved one feature. Sometimes we call it a predictor. Now in this unit, we said, what if we have several features, d of them? We came up with this multivariable linear model that handles d equals 1, but it also handles d equals 2 or any finite number. So the question now is there an advantage to this over this? Is this one always better than this, or sometimes? Do you have an answer or a question?
Well, yeah, when you want to kind of compare them with an adjusted R value, so you can tell if the added complexity of the calculations is actually worth it.
So let's not talk about complexity here. Let's not worry about that. Let's just worry about performance. And I just want to take a vote. How many people think that this is always better? And don't be shy. Okay, only a few people. Okay, and how many people think that this is always better? Okay, somehow. Okay, what about is this? Does it depend sometimes? How many people think it depends? Okay, for those who said it depends, do you have any insight into what you mean by like when might it be better to do the top one?
I mean, I don't know if this is what you're getting at, but my thought process is, there may be, you may have one, feature that is pretty decent at predicting a linear model, but then you add in a bunch of other features and including with that original feature, and it just kind of dilutes the effectiveness of the model. It seems like just something that you would have to use some intuition and try and error. and figure
Okay.
out.
So the way that I pose this question, it's not really clear what the answer is because there's something really important that I did not clarify. Is the criteria? What do I mean by improve on? Like, what's our criteria exactly? So let's be a little bit more careful about this. If I said the criteria is to minimize RSS on the training data. So RSS in the way that we've defined it in units 1 and 2. If that is a criteria, would anybody change their votes? Does anybody feel like, okay, how many people, if that's a criteria, say that this one is always going to be better? Okay, how many people think that this one still might be better? Okay, so it turns out that now, in the case that all we care about is training RSS, it turns out that this one is always at least as good, but usually better than the first. So this idea about, like, if you have some strong features and weak features, and somehow, like, the weak ones are corrupting the strong ones, well, it turns out that multiple linear regression, because it's least squares optimal, it's doing the right thing. If there's a really bad feature, or if it's like somehow, conflicting with some other ones, it's going to merge all the data in the right way for how we set it up, which is to minimize RSS. It's going to do the perfect thing. What's tricky is that in practice, minimizing the performance on your training data is not exactly what you want to do. What you really want to do is you want the performance on data you've never seen to be good. And it turns out when that is the criteria, then the situation is very different. We're going to get into this in the next unit, but basically in that case, it is true that some of these features cause more noise, if you will. It's better to actually ignore them than to try to use them.
So multiple linear regression might end up being like too optimized to one data set?
Yes, you could say it that way. It overfits to your training data.
And so when you say there's, in this circumstance, maybe multiple linear regression does start of, you said corruption, maybe I said it, I don't remember. But that only happens when you're looking at predicted values. I'm a little lost.
So it's sort of a matter of which data set are we talking about doing the prediction on. If we're talking about using our training data set, we train on that and then we measure performance on that same training data set, multiple linear regression is the way to go. It's that when you train on one data set and then you test on some other data set that was not the one you trained on, now that's a different, more complicated problem. And that is a problem we're going to get into in units 3 and 4. So I just wanted to kind of put this out as a teaser, but I'm not going to get into too many details right now. So for right now, we're going to focus on just the training error alone, and we'll do an experiment with our diabetes demo in that we will go through the data. In this case, there's 10 different features. We will use each feature on its own individually in the style of Unit 1, and we'll compute the R-squares. So the code is very straightforward. We have a for loop that just goes through one feature at a time, and these are the simple equations that we derived in Unit 1, where we have these like scalar statistics and so on, and we can compute R-squared. And this is what we get for the different features 0 through 9. Here are the R-squared values. So when you look through these, you notice that some of these features on their own are almost useless for predicting the target. Like this one has an R-squared of 0.001. So this is really doing a terrible job. On the other hand, there are a couple that are more successful, like this is 0.343, the second best one is 0.320, and so on. But if you look at any feature individually, the best you can do is 0.343, 3.439, whereas if you look at them jointly all together and you use least squares to combine them in the right way, you get 0.51, which is better, right? So here you do see the strength of doing things jointly with this multiple regression model. Now again, to be clear, we are computing R squared on the training data. That is our objective. That's the same data we trained on. So in this case, things will only, they'll be no worse. Generally speaking, they're better, but in extreme cases, it could be equal. You could have you could come up with a pathological example where all the features in your data set are identical. So obviously using one or using them all is going to give you the same result. But in general, when they're different, multiple linear regression is going to work better. Okay, so that is just sort of a comparison of these two approaches. Any questions on this? Yes.
I don't grasp how the multi does better when you have, when we're looking at that data, the single does far worse than the multi.
Yes.
I don't guess, mathematically, how it's doing better. Sorry.
Well, I mean, I think it's not too crazy to think that if you take in several pieces of information and process them together, that's, just in life, right? Like you take in a few things together and synthesize them, then that's better than looking at them one at a time in isolation.
It's kind of like data fusion when you have multiple
Yes.
sensors.
It's fusing all the D features together in the way that's mathematically optimal for R squared. For RSS, minimizing RSS maximizes R squared. So it's doing the absolutely best thing that you can do. Yeah. Okay. Any other questions? Okay, great. So now let's just do sort of, again, as a teaser, a little experiment where we take our training data, which is 442 samples altogether, but we split it into we partition it into two subsets. One, which we're going to, okay, so maybe I said it wrong. We take our whole diabetes demo data, which is 442 samples, and we're going to split that into two data sets. The first data set we're going to use to train our model. That's going to contain 300 samples. The second data set we're going to call the test data. That will be the remaining 142 samples. These were never seen during training, so they're sort of like an independent way of evaluating how well our trained model worked. So you can see we're going to create an X-train matrix, an X-test matrix, a Y-train vector, and a Y-test vector. And the way we're doing that, we're just starting with our big X matrix, and we're taking the rows, the first row, all the way up to, but not including this number, NS train, which is 300. Now, we use regression fit. We give it the training quantities. When we do prediction, we're going to do it two different times. First, we'll predict on the training data. Second, we'll predict on the test data. And so now we have either the training labels predicted or the test labels predicted. And we go through a few other lines of code, and we can compute the R squared on the training data, which is again 0.51. It's not exactly the same as it was with 442 samples, but it's close. But what's interesting is that on the test data, it's just a little bit worse. And that's typical, because usually there's a bit of a mismatch between the statistics of these data sets. And so you really optimized on the first one. That's where you expect to get the best performance. And this other one, which is just slightly different, it's just a little bit worse. So that's what you tend to see in practice. Okay, and we'll dive more into this in future units. Any questions on what we're doing here? Okay, good. And then there's one more subject I want to talk about today, which is very useful in moving beyond feature data that is purely numeric in the way that numeric sort of in the way we've been handling it until now. So an example is, let's say I want to predict the miles per gallon of a car, and I'm using the horsepower. I'll call that, so miles per gallon, let's call Y. Horsepower, let's call that X1. But now let's say I have the brand of the car. And the brand is not a number. It's either Ford, Honda, or BMW. So the question is, how do I do this? So the sort of naive approach would be just like assign a number to each brand, like 1, 2, 3, 1 for Ford, 2 for Honda, 3 for BMW. And then now you have a numeric data set. You can, handle it just like we've handled it until now. So what do you guys think about this? Is this going to work? If not, maybe why not? Why is this not going to work so well?
Giving them values gives them an order.
Exactly.
So one seems further away from three than it actually is.
Exactly. So we're sort of imposing an order because 1, 2, and 3 are ordered, and so we're sort of imposing that in some sense, Honda is twice Ford and BMW is 3 times Ford and so on. And okay, maybe there is some way in which that makes sense, but in general, for predicting our miles per gallon, it probably doesn't make sense. So if you did this, you would get a prediction, but it probably would not work very well. So we want to avoid any ordering between these 3 categories. And so the trick that's usually used for this is called one-hot coding. And one-hot coding essentially represents brands not by these integers 1, 2, 3, but by binary vectors. So this is what I mean in this table. Essentially, instead of coding x2 as just some integer or floating point number, let's say we split it into 3 pieces. We get rid of the original x2, we replace it by these 3 things. So now we actually have 3 separate features. And they take on the values either 1, 0, 0, 0, 1, 0, or 0, 0, 1. So in this sense, there's now no longer any ordering between them. It's just like they're all kind of equally different. And to do our model, we're going to do it this way. So just as before, we have an intercept. Just as before, we have our horsepower times a beta 1. But now we have these 3 new features constructed in this way, and we will just give them 3 separate coefficients, beta 2, beta 3, beta 4. I could have called this beta 2 sup 1, beta 2 sup 2, beta 2 sup 3. But I didn't, just because I want to pack these betas into a vector just like before, and in that sense it makes it a little bit cleaner just to give them 2, 3, 4s. Also, I could have called these x2, x3, x4, but I didn't want to be confusing with this already defined x2. But hopefully you get the idea. With this new model, we now have a new approach where I do have numerical values for all my features. It's just they've been chosen in a way that makes these 3 brands not ordered. Okay, so is everybody clear on what we're doing? So the next thing is to describe what actually happens when we do this. So what happens, we can figure this out, but by just saying, okay, anytime I get a Ford sample, remember this is the coding for Ford, I'm going to get a 1 here, a 0 here, and a 0 here. Because of those zeros, essentially those terms are not present in any Ford samples. So for all Ford samples, I have a model that looks like this, where again, these betas are trainable parameters. Now imagine that instead I have a Honda sample. So for the Honda samples, based on the coding, I'm going to have 0, 1, 0, which means these guys are not really there. And I have this model. Okay, and then similarly for all the BMW samples, I will have this model. So, across the BMW samples, I'm of course going to have different versions of X, 1, and Y, but other than that, they will all have this form. Is it clear how this implies this? Any questions on that? Okay, so now that you have it distilled down to here, you can see more what's actually going on. You can see that essentially, for the Ford samples, your intercept term is really beta 0 plus beta 2. That's the constant offset. Meanwhile, for your Honda samples, your intercept is beta 0 plus beta 3. And for your BMW, it's beta 0 plus beta 4. Because you have independent control over all these variables, it essentially acts like you have a different intercept for Ford versus Honda versus BMW. You can actually train 3 different intercepts that are brand specific. Okay, so that is the interpretation of what's actually happening when you do this. One-hot coding is actually sort of allowing you a different intercept for every category. Okay, so is that making sense? Okay, so that's That's definitely what's happening here. Now, yeah, go ahead.
Slope is gonna be the same no matter what.
The slope is exactly the same. Yes, you can see that. So everybody gets the same slope. All brands get the same slope, but brands get different intercepts.
So this is limited because it doesn't adjust.
Well, we just kind of started with this idea,
Oh,
and we saw that this is what's happening. But you make a great point. What if instead you wanted to actually have a different slope for every brand and maybe the same intercept? So we could do that too. We just have to change up the strategy a little bit. So that's what we'll talk about next. We'll call it one hot coding of slope. We'll use exactly the same coding scheme, but we'll just make the model, we'll use them slightly differently. So in this case, we're going to multiply this beta 1 x1 by this binary number, multiply beta 2 x2 by this next binary number, and multiply this by the third one. So using the same logic as before, like when you have a forward sample, you get 1, 0, 0. So those go away, and you get this. For the Honda samples, you get 0, 1, 0. So those go away, and you get this. And for BMW, you get that. And so now you can see, oh yeah, we get a different slope, but the same intercept for every brand. Okay, so it's just another way to do one hot coding. The right way is not exactly clear. It sort of depends on maybe if you have some knowledge of your data set. If you're saying, well, like back to this miles per gallon prediction problem. What if you are saying that I don't think these manufacturers rate horsepower in the same way. When Ford tells you the horsepower, they're using this one system. When Honda does it, they're cheating. They're giving you like a rosy picture of the horsepower by doing this slightly differently. And then you say, so I can't really treat them equally. I really need to interpret them differently. I really need to learn an independent parameter for each brand of car. So that would be, a valid place to do this. You could also say, well, I actually think that both the slope and the intercept should be brand dependent. But if you do that, what's happening in this case? Does anybody see? What's another way of tackling that problem?
well, I don't know about the other way of tackling that problem, but I imagine you might as well just separate the data.
Yes,
sets.
you may as well just like take your Ford data, do prediction on that, take your Honda data, and so on. And so, what do you think the weakness of that is? Any idea? Not exactly. But
There's no correlation between the features and the output.
yeah, in some sense, you don't get the benefits of aggregating all the data and using all this data together. You're sort of just breaking it up in pieces, and so if the pieces really should be independent, that's what you want to do. But usually, looking at a larger data set and trying to exploit similarities and correlations and stuff over the larger data set is going to be better than breaking it up into small pieces. So you sort of lose something when you do joint slope and intercept coding over everything. Okay, but in any case, it's just good to understand what's happening when you take these different approaches, and once you understand what's happening, then you can try these different things for your data set. In fact, you could train each of these models, and you could look at the RSS on the training data as a way of seeing which one fit the data the best, right? Now, the trouble with doing that, as we'll see in the next unit, is, again, you'll do great in your training data set, but that doesn't mean you're going to do great on some unseen test data. So at the end of the day, that's not actually a good strategy, but like based on what we know now, if we really only care about training RSS, then that would be a good way to go. Okay, so that's one hot coding. Any questions so far? Okay, there's just one more thing to talk about. Is that when you do the one hot coding of the intercept, which is the first strategy we talked about, there's a little bit of an issue with respect to how I told you we should do it. I'll try to clarify why that is, but essentially what happens is when you do it the way that I showed you 2 slides ago, it will make this matrix non-invertible. And we might not want to do that. So let me explain why this is. So we're back to the case of coding this way and modeling things this way. So here we have these new beta coefficients applied to our binary one-hot coded variables. And so when you look at these beta vectors that contain all 5 coefficients, they will all have one of these 3 forms. So anytime you have a Ford sample, they will have this form. Anytime you have a Honda sample, they'll look like this. Anytime you have a BMW sample, they will look like this, right? Because the first 2 columns are the same, and then the 3 columns at the end are just what we have in that table. So there's one way to see the problem is I can be very clever, and I can dream up this sort of adversarial vector. And notice that when I take the inner product of this beta vector and any one of these, I get exactly 0. Right? Because what happens is this is 0 kills x1 no matter what x1 is. And the rest of these ones will always combine with these in a way that also cancel to give 0. So essentially, beta times any row of the A matrix will give you 0, which means this A times beta as a whole vector will be zeros. And if this is 0, then I can multiply this on the left by A transpose, both sides of the equation, and I will also have this being 0. And so now, if you have any matrix such that you can find a non-zero vector where when you multiply it by the matrix you get 0, this is a sign that that matrix is not invertible. The way I like to think about this is if you think about the matrix as a black box that accepts a vector and outputs another vector, this black box has taken in something that's non-trivial, some vector values, and has squashed it to 0. And now I've lost information. For example, if I would have given it 2 times beta, by linearity, I would have also gotten 0. So now, essentially, this black box has made it impossible to tell whether the input was beta, 2 beta, 5 beta. Right? There's no way to get it back. If there's no way to get that information back, it's not invertible. Invertible would mean from this, you can always get back this, and that has become impossible. So because there's a non-zero vector such that A transpose A times a vector is 0, we know this matrix is non-invertible, and therefore when we want to use it in that A transpose A inverse thing, it no longer works. So this is related to the fact that what we did over here was actually kind of redundant. We have 3 intercept coefficients, right? But we're actually using 4 different numbers to get those 3 things. There's like this extra degree of freedom that we don't really need. That's what's causing us problems. So there's a couple ways to do it. One way would be just get rid of your beta 0. Another way to do it is to come up with a slightly different coding scheme where you have just these 2 columns. So you have now 2 binary variables. They're either 1, 0, 0, 1, or 0, 0. Either of these approaches will work to avoid this issue we have caused here. Another issue that we'll talk about, or another approach we'll talk about to solve this problem, is to use a slightly more sophisticated way to do our modeling, something called regularization. That's another approach. But I think the recommended approach is to use something like this, or setting the beta 0 equal to 0, something like that. It's just a bit cleaner. Okay, so any last questions about one-hot coding? Okay, and then just sort of as a motivation for what we're going to do next, and sort of to, again, try to sell you on linear methods, is on one level, linear methods seem really weak, but I want to show you an example of something else clever you can do. Let's say you wanted to do polynomial modeling. And when you look at this, that means we take x to all these different powers. That would be like you have a scalar x, you now make a polynomial out of it. And with a polynomial equation, you can get all kinds of crazy prediction curves. Like they're no longer lines, they're these sophisticated curves. So, and the reason why you might want to do this is because maybe a line doesn't fit the data, but a curve will, okay? So the thing to realize here is even though we have a model that is nonlinear with respect to x, it is still linear with respect to your beta coefficients. And that means that we can still use all the machinery we developed in this unit without any issue at all. In fact, all we need to do is take our scalar x raised to the power j and then define that as the jth entry in some vector x. And so now this is just like x1, x2, ... xd, and now we have just standard linear, multivariable linear regression. And of course, this is not the only way you can do it. Like you could have all kinds of crazy nonlinear models like cosine omega j times x for different omegas. You could assign those to your different xj's. Now this is, again, nonlinear x. So there's all sorts of things you can do. And so really, linear strategies can be very powerful if you combine them with nonlinear processing, either on your features or on your targets. You also saw that at the homework due today. The last problem was another example of that. So we'll return to this in the next unit because the key question, once you start to do this, is, well, D is now a design variable, right? Like, where do I stop? Do I do a quadratic model, cubic, quartic? Where do I stop? And so here we get back to that question is, again, is more features better? And yes, if you want to minimize training data, the answer is, yeah, you use as many as you can. But if you actually care about how it performs on unseen test data, we'll say the answer is no. More features is not necessarily better. Some of these features can cause you more noise and than actually be productive. So that's kind of the transition to what we'll do next week. So have a great weekend. I'll see you guys on Monday.